I teach 30 stars, but 7 stars here were shining so well last night. Cats on 2! 1, 2, cats! Yes! My first game ever. Ever. I've never attended any kind of game before. Nowhere. That was the perfect one to actually start the thing. Awesome. This guy should change his legal name from Asser to General. 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 Swear to God, he takes care of everyone. Really, really, really great guy. And the best movie ending was when Drilling got the 2 shots. They sucked with their shots. Seriously, they threw so many shots, they only got one. One in the entire game. Seriously, like we fought to win. Oh my God, like we were aggressive, like we wanted to win. Seriously, they honestly they didn't. I didn't know. I didn't get that much soul. We had it. We had it. And when this guy gets the ball and gets the center mass down, that's it. That's it. He's there. I'm like, where did he? Speed of light? Forget about that. Speed of Ali. It was just so much fun. Okay, so today we do what's known as the there we go. Universal wave equation. Okay, so before we even cover it, don't copy anything. Okay, does anyone know this guy? Speedy Gonzalez. This is my childhood, right there. Why is he called Speedy Gonzalez? Because he's very what? He's super, super fast. Okay, so there we go. Speedy Gonzalez. Okay, so probably everyone knows this one. Now, I don't think anyone knows. So what is this? It's a horse. This is not just any horse. This horse's name is Secretariat, like a secretary. Yes, sir. That was the actual name. This is the most famous racing horse of all time. Okay, won the Kentucky Derby, won so many races, and so on. Okay, they even made a movie like, yeah, that's Craig Ferguson with his Secretariat on the show. Okay, so very simple question: who would win a race between these two? What does Speedy Gonzalez have that Secretariat doesn't have? A smaller mass. Interesting. Okay. What does Secretariat have that Speedy Gonzalez doesn't have? Long legs. Okay. Question. How big is Secretariat's stride length? Small or big? Big. How about Speedy Gonzalez? Okay. Now, how many steps can Speedy Gonzalez take in a second? Did you see what we did here? One of them has the what? Has the big what? Wave. No, not the amplitude. One of them has the big what? Wavelength. Okay, peak to peak. Imagine the heels are the peak to peak. But they have what? Low what? Low frequency, right? Because it takes them time to what? To do a single hop, right? Speedy Gonzalez has a very small what? Wavelength, but a high what? High frequency. So that means what? Either one could win depending on what? If their frequency is what? High, or if their wavelength is high. Is it making sense? So we wouldn't know until we actually what? Until we actually put some numbers to it. And that's basically what the universal wave equation is. So when discussing how a wave moves through a medium or even through space, it doesn't matter. Remember, wave is wave. Okay? There's a very important equation to be considered. It is called and focus on the word universal. Universal wave equation. This equation that we're going to learn today literally applies to any wave in the universe, no matter how advanced, how complicated. Every wave obeys this equation, the universal wave equation. Okay? Now, what does this equation have in it? Like, what does it relate? What quantities does it have in it? 3 things. By the way, it's a super easy equation, yet it governs pretty much all of waves. It relates, or it includes, wave speed. How fast it what? Remember, waves really don't move. What actually moves? The particles inside of the medium that carries the wave. The wave itself is the energy moving through the medium. So how fast it appears to be moving. So that's obviously usually what we want to calculate, the speed of the wave. Okay, number 2, wave frequency. How repetitive or how repeating but the word is repetitive. How repetitive it is. How repetitive it is. What was the third factor? Wavelength. How long is the stride length of each animal? Wavelength, or how compressed slash what slash stretched the peak to peak distance is. These are the three things. That's it. There's absolutely no more factors or parameters, as they say, to the wave equation. Okay, what is the equation? Super easy. Everyone? That's it. Wave speed equals the multiplication. Come on. The multiplication of what? The frequency and the wavelength. That's it. No square roots, no half mv squared, no squaring, nothing. Literally, speed equals frequency times wavelength. By the way, this is the same mathematical structure as what? The triangle for the distance and speed and time, which in mathematical terms would be this. Done. That's the universal wave equation. Is this a math or a physics equation? Oh, but okay, technically all equations are what? Math equations. But is this a physics equation? Yes, because that's not like the what do you call it? The radioactive decay one. This needs standard units. So what should be standard for wavelength? Length, meters. What should be standard for frequency? Hertz, so per second. And then you are guaranteed to get your speed in what unit? Meters per second. You got it. If you do not convert the units to the proper ones here, sorry, something is not going to be 100% correct at the end of the solution. Okay, so all of these units have to be standardized. And again, this unbelievably simple equation is the cornerstone of atomic physics, optical physics, and electromagnetic theory. Why? Because light is a what? Light is a wave. So basically, when Einstein actually came up with the theory of relativity, both the special and the general, he actually used this equation. The frequency of light, the wavelength of light, gave him the speed of light in vacuum. Yes, this appears in any advanced physics book. Okay, let's do a couple of easy demos, I guess. I mean, what's okay? How many variables do we have in this equation? 3. So I have to give you how many, and ask you for the third. And what's the worst thing you could have to do? You would have to divide either speed by wavelength or speed by frequency to get the other thing. Okay, so let's go to the next slide for the demo problem. Okay, a wave has a frequency of 230 hertz. So what does that mean? If you watch it, you can see that a peak bobs up and down 230 times in one single second. In one single second. And have a wavelength between peak to peak or bottom to bottom or whatever, two identical points of 2.3. What's the speed? What do I just do with those numbers? Is everything standardized already? Yeah, hertz and meters. We're good. So you just go V equals F lambda, which equals to 230. Yeah, times 2.3. 23 times 23. Think about it, everyone. This could be 23 times what? Times what? 10. And then I'm going to steal this 10 and multiply it by this one. So it's 23 times what? Times 23, which is actually 529. But obviously, to what? To 2 sig figs because of this one and that one. You have got to make it 2 sig figs. So it's actually done. Let's do the next demo problem. A wave now has a speed of 1500 meters per second. So that's how fast you see the peak move, like in a lake or an ocean or something. And you know it has a frequency of how much? How would you know that? There's like, for example, a plastic duck, and it bobs up and down. How many times in 1 second? 11 times per second. The question is, how far are the what? How far are the two wave? So how far is a wavelength, or how far are the two peaks? By the way, I usually say peaks. I could say what? Valleys or bottom, but I usually think of it as two peaks moving together. Okay, am I going to multiply or divide? I have to divide. So let me just write the equation first. V equals F lambda. Which one of those 3 variables are we asked for? lambda. So that means lambda equals this one, as the triangle says here, V over F, which is what? 1500 over 11. Well, that's slightly less than 1500 over 10, so it's less than 150. What's the answer to a few sig figs? 140 what? Sorry, 130. So 136 point. Oh, so it's an infinite number of 36. So the 136.4 meters per second, or just meters? Just meters, because it's a wavelength, and you already have meters per second, so you can't have it again. But this is 4 sig figs, way too many. If you cut it here, what does it become? 140 meters. So the peak to peak, traveling all the time, is what? Is that. So if you see a sitting plastic yellow duck, and you time it, you're going to see that, obviously, if you're a fast counter, you would count 11 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in what? One single second. That's what the frequency of the wave is. How many things repeat in what? One single second. We're good? No, so the wavelength, by the way, this is a moving wave, right? So you're sitting on the side, everyone, you're sitting on the side, and you watch one peak move. Okay? You watch one peak move. Apparently, when you watched it move from here to here, in one single second, the peak crossed 1500 meters of space. Is it making sense now? So peak speed is 1500 meters. Peak up and down is what? 11. You can always then know what? How far two peaks are. That's exactly what we just. Let me show you a quick animation to show you what that means. Okay, everyone. Are they moving together? Okay, I want you to correspond the compression area. Is it always moving with the peak? So can you always look? This one's always corresponding to what? A peak. And this one is corresponding to a what? A valley or a bottom. By the way, the two names from your notes yesterday are, we could call it peak, but what? Did anyone look at the notes from yesterday? No. By the way, you could call it max and min. That's what math people like to say. Physics people like either to say what? Peak and valley, or crest and trough. This is a crest, like this toothpaste, and this is a what? A trough. Okay? You know what? I'm going to keep calling it peak and valley. Question: does every compression stage correspond to a peak? Okay. Does every expansion correspond to a bottom? Are they always moving together? Does that tell you that you can always model or represent any longitudinal wave as a transverse wave? Yes, you can, all the time. You know why? Is this low density or high density? There you go, high. How about right here? Lowest. You can always model any longitudinal wave as a what? As a sine and cosine wave. That's why any periodic, the invention or the actual field of trigonometric functions like sine and cosine waves in grade 11 and grade 12 was one of the most important achievements of humanity. It made us able to what? Model or represent or study anything that repeats itself, whether it looks like this or looks like this or looks like a what? A spinning circle. Anything could be represented as a what wave? As a transverse wave. By the way, some people like to call it sine wave, but it could be a cosine wave as well. So let's just call it a transverse wave.